Okay, it's a conditional statement. Yet another way to make a conditional statement in English is to refer to the antecedent as a sufficient condition for Q. When we say if P, then Q, we're saying P is enough for Q, or P is sufficient for Q. So, that number 21, that's A horseshoe B. It's saying A is a sufficient condition for B. That's the antecedent of a horseshoe, the sufficient condition. Look at number 22. Necessary condition. Okay, the consequent of a horseshoe is the necessary condition of the antecedent. So, necessary condition refers to the consequent. The translation of number 2 is A horseshoe C. Oops, no it's not. It's C horseshoe A. A, the necessary condition, is in the consequent position. So some people just prefer to remember that as the sun theory of the conditional statement. Antecedent is sufficient, consequent is necessary. Okay. I wouldn't be too worried about all this because we have like a millennium before test 2. It's way too much time, if you ask me.
That was an evil look.
Just want to introduce our first proof procedure. Then maybe a quick break. Have a look at your test. This is in 8.6 of your book. This is called the long truth table, proof of validity or invalidity. Now, typically, our arguments, either when we translate them from English or they're presented in the book, they're written vertically. But to set up the argument for this proof procedure, the first thing you do, and you would be doing this on your scratch paper, because I'll present it like that in the test. On your scratch paper, you simply rewrite it horizontally. And you separate the premises with commas. And the last premise from the conclusion with a comma. And use our 3-dot symbol for therefore. All right, when we introduced the symbolic language, I had columns of T's and F's, under the component statements. That's called a truth table. So the first thing we want to do here is show all possible combinations of truth values for those two simple statements, A and B. Well, where do we get those columns of T's and F's from? There's a simple formula that you use and you must use to derive those columns, and in this case, rows of T's and F's. The formula always begins with the numeral 2. What that 2 refers to is the number of truth values in the universe. There are 2 of them. T and F. Then you want to raise that to the power equal to the number of component simple statements in your argument. There are two unique simple statements in our argument, A and B. Doesn't matter that B occurs twice. Doesn't matter that A occurs twice. There are two unique simple statements. So in this case, we're going to square 2. If there were 3 of them, we would cube 2. If there are 4 of them, we would raise 2 to the 4th power. Okay? In this case, we're going to square 2. The first value that this formula gives you tells you how many rows of T's and F's your truth table is going to have. Rows moving left to right. So I'm going to number them. Then you divide that by 2. The next value the formula gives you, in this case 2, that tells you what your first column is going to look like. The column of T's and F's under the first simple statement. 2 means you're going to alternate T's and F's by 2, always beginning with T. So the column under A is going to look like that. Now, sooner or later, you have to reproduce that column under every other occurrence of A. You can do it now, or you can do it later. Because it's the same simple statement. If it's true, it's true. If it's false, it's false. You have to make sure you have the same column under every occurrence of A. I'm going to go ahead and do it right now. Back to our formula. You continue dividing by 2 until you determine the column under the final unique simple statement. Well, we're there. There is only one other unique simple statement. It's B. Okay, so that value, 1, that tells us to alternate T's and F's under B by 1, always beginning with T. Now I reproduce that column under the other B. So what we have here is every possible combination of truth values for those two simple statements, A and B, in this argument. Now those are called the initial guide columns. They're initial because they're the first ones that we complete, and they're the guide to all the remaining columns. We only have one column to complete, that of the horseshoe in the first premise. So you have to refer to your definition of a horseshoe. When is it true? When is it false? You have to know that. The horseshoe is only false when the antecedent is true and the consequent is false. Otherwise, it's true. We've now completed our truth table. It's ready to be interpreted as indicating validity or invalidity. See, this is an analog to our Venn diagram. See, we diagrammed the premises and then read it, we interpreted it. See what becomes of that conclusion. Well, this is a little bit more complex. What we're looking for is a row, at least one row, that is invalidating. What is that? True premises and a false conclusion. See, that's not possible in a valid argument form. These are all possibilities. So if it's possible in this argument form, it must be invalid. Now, I'm going to take away all the T's and F's we're not concerned about right now. See, that is the truth values of the first premise. And our second premise is simply A, and our conclusion is B. I'm looking for at least one row in which the premises are true and the conclusion false. not there, not there, not there, and not there. It is not possible for those premises to be true and the conclusion is false. Because these are all the possibilities. Therefore, you read this, you interpret this truth table as indicating a valid argument form. Let's look at a truth table of an invalid argument form. Okay, we have to complete our initial guide columns according to our formula. We're going to begin with 2. Why? We always do. And again, we only have 2 unique simple statements in our argument, A and B. So again, we're going to square 2. Anybody remember what that first value indicates? In this case, 4. What does that tell you about your truth table?
The number of rows.
The number of rows from left to right. Then you keep dividing by 2 until you determine the column of truth values under the last unique simple statement. But again, this is going to come to a close real quick because we only have 2 simple statements. So after the first division by 2 tells you about the first column. That says alternate T's and F's there by 2, always beginning with T. So here's our column under A. Sooner or later you have to reproduce that column under every occurrence of A. I'm going to go ahead and do it right now. And then back to our formula. When we divide by 2 again, that's going to tell us the column under the next, in this case the last unique simple statement. So B's column alternates T's and F's by 1, always beginning with T. Now we reproduce that under the other occurrence of B. Those are our initial guide columns. Now we need to complete the table. That means every symbol has to have a column of T's and F's under it. You complete one premise at a time before moving to the next, and all the premises before the conclusion. We only have one symbol remaining in our first premise. It's the horseshoe. It's only false when antecedent is true and consequent is false. Our second premise is a curl. The curl, by definition, has the opposite truth value of whatever statement it's negating. So where A is true, curl A is false. Where A is true, curl A is false. Where A is false, curl A is true. And the same thing for the negation of B. It's not going to be the same column, but you're still going to reverse, in essence, the truth values of B. So our truth table is complete. Now we have to interpret it. What are we looking for? We are looking for at least one row. I don't care if there's 100 of them. It's sufficient for a proof of invalidity if there's at least one row on which the premises are true and the conclusion is false. Let's see. I'll take away the truth values we're no longer concerned with. Not there. Not there. Oops. an invalidating row. It is possible for an argument of this form to have true premises and a false conclusion. Therefore, it's an invalid argument form. Please notice, that doesn't mean anything. I mean, some students think that means it's valid, because everything is true. That's not what validity means. Validity means this is impossible. Since it's possible in this argument form, that argument form is invalid. Please note, if it didn't occur to you, there is no positive identification of validity. There's nothing to find to prove the argument form valid. See, it's the absence of any such row as this that proves validity. It's the absence of any such row. Okay? Now, just a couple more things. First of all, I'm sorry, but your author constructs these truth tables a little bit differently than I do. So when you look in the back of the book, or maybe even on eLogic, they're not going to look the same way. I'm going to show you what he does, and I think you'll agree that my way is better. He has the component simple statements out here on the left, and he constructs his initial guide columns there. Then, to complete the columns under the other symbols, he has to keep referring back to these. Back and forth, back and forth. So, for that horseshoe there, you'd have to refer to these and say, okay, that's true. There it's false. There it's true. There it's true. I'll tell you a couple reasons why that's bad. These can be really long. There might be several simple statements. They might occur in different orders than they are listed over here. So it adds the confusion of what am I using to determine the truth value of some symbol. Here's another reason why it's not good. Okay, we might have an argument with those two horseshoes in them. Now, it's not much of a problem to determine the truth value of that horseshoe by referring to these. But a lot of students forget that B here is the antecedent. So this is not when that horseshoe is false, right? Because this says B is false and A is true. That's not a false horseshoe. This is when that horseshoe is false. Confused? Good, you should be. Because his method is hinky. It's not good. So we'll do it this way, the way we're doing it in class. The last thing I want to point out to you. Let's say that's a premise or a conclusion, okay? And let's real quickly put our initial guide columns there. Okay, to complete the columns under every symbol in this compound statement, you obviously have to begin with the initial columns under the letters. But then you have to find the next most complex symbol to proceed to. By next most complex, I mean, you could look at it this way. What symbol can I now determine the truth value of given what's already up there on the board? Well, there are 3 symbols remaining, right? And I would say 2 of them can be done at this time. that curl, because it's a function of A, which you already have, or that horseshoe, which is a function of A and B, which you already have. You can't determine the truth value of that wedge because it's a function of the horseshoe and the curl, right? So these two symbols they have equal claim to the next most complex symbol. It wouldn't matter which of those you did first, but they would both have to be completed before the wedge, like so. Oops. Now, that wedge, its truth value is a function of what symbols? On the left, which column am I referring to?
The middle one.
The horseshoe. And on the right, what column am I referring
Just a curl.
to? The curl. So that's what we're looking at here for the first truth value of the wedge. That's a true wedge. That's a false wedge. That's a true wedge. That's a true wedge. That's all you need to know to knock yourself out until next Tuesday.